Since the beginning of the space age, humanity has united in the search and quest for the knowledge of space, representing the ultimate voyages in adventure and discovery in much the same spirit as Columbus, Magellan, and the pioneers who settled the wild west of America, with that bold curiosity for the adventures that lay ahead. This program looks at the future of humanity in space and the places throughout the solar system we might just visit over the next 50 years. From the very beginning of space exploration, satellites, probes, and robotic spacecraft have been our eyes and ears to the universe. Perhaps the most spectacular photos taken of our solar system were those taken by the two Voyager spacecraft. The Hubble Space Telescope has in fact shown us no less than the virtual edges of the universe.
For the first time in history, if you have any children, you can open up a book and show them pictures of the other planets. They're not little dots in space. They're not points of badly focused light. They're actual objects which have dynamic histories and which you can in fact see and talk about as a visitor and look at the wondrous, strange things which are there. So for the first time, our society has produced a tour guide book to places of the universe that human beings had never seen before, could only imagine or hallucinate about before.
Perhaps one of the most important aspects, though, is just for the youngsters. That is, I think space represents a future of opportunity, an opportunity to learn something new, an opportunity to do something new, an opportunity to go somewhere nobody has gone before, at least for our sensors to go there, and an opportunity, really it's a future of opportunities to do something nobody's done before.
And when you're exploring the solar system, you have a view of the Earth, and one looks at all of these as relatives, as what could happen in a planet, and then you get to look at the planet in wonderful ways which you never would have had happen if you stayed home. In fact, I'd say there was a very interesting thing in looking at the atmospheric pollution problem. The first clues to the dynamics and chemical kinetics of atmospheric pollution and acid rain and the processes which cause very unpleasant things in the atmosphere were the studies of Venus.
It's very clear that comparative planetology is extremely important. I think that both in the area of atmospheric science and geology, the evolution of the Earth will only be understood if we compare it with the evolution of the sister planets Venus and Mars.
And by studying the other planets, we can better understand the processes which have shaped those planets and which have shaped the Earth and are continuing to shape the other planets and the Earth in the solar system. Of course, along the way, in order to meet the challenges of sending our ears and eyes and our sensors out into deep space, we have to do things nobody's ever done before technically. And that technology becomes available for use in everyday life. And there are many examples of where the technology we've developed in order to go into deep space are now used in commonplace activities.
Over the next several years, there will be an armada of robotic spacecraft from several nations that will photograph and study all parts of the solar system. The Japanese space agency ISIS has plans for at least 3 major missions.
We have a series of missions to the solar system. Well, the first, next year, we are going to have the Lunar A mission to study the interior structure of the moon, and then plan to be to the Mars 98. And then we shall have a mission to the asteroid Nereus. The launch is planned for the early 2002. So these are the 3 planetary missions which are addressed to the moon, Mars, and asteroid, so that at this point we are expanding our coverage. And after seeing what we have achieved with the Planet B mission, we shall think about what to do after these 3 missions.
In the spirit of international cooperation and collaboration, the scientific information that comes from such explorations of the solar system are shared worldwide among scientists.
The data which are obtained by Planetary as well as DONNA A will be studied internationally. As is the case in the scientific explorations, principal investigators who build the instrument, of course, have the priority. So it's always the case that they are the first to look at the data and do some analysis. But eventually, data will be opened to public so that every scientist in the world can look at the data together and work together.
The European Space Agency, ESA, comprises a partnership of several European countries and takes part in explorations of interest to all of its partners.
In Europe, solar system scientists divide the objects in the solar system into various categories. One, of course, are the planets. The others are the small bodies. And small bodies generally includes comets and asteroids. And ESA is just concentrating on the study of comets.
Recently, ESA launched a very successful probe to study Halley's Comet. This probe acquired a wealth of information about comets and their composition, structure, and evolution.
Now ESA is just going out to launch in 2003 a spacecraft towards another comet, but for a rendezvous mission to really go around the comet and stay with the comet, follow the comet from about 5 astronomical units down to 3 astronomical, and see how the comet develops, how it evolves and emits gas and dust and things like that.
In the next 15 to 20 years, the American Space Agency, NASA, is planning to launch 2 very different types of space probes to other planets. The first type of spacecraft is the big-budget, multi-billion-dollar satellite that will serve many functions during its lifetime and bring back vast amounts of information and photos. One such satellite is Galileo.
The Galileo spacecraft is in orbit around Jupiter, having dropped for the first time a probe into the atmosphere of Jupiter, returning information about what this giant planet is made of, what kinds of molecules, what the temperatures and pressures, where the clouds are there lightning, well, we know there are lightning bolts, but to monitor the lightning and to detect how much heat is coming up from the interior of this giant planet.
The Galileo spacecraft will remain in orbit around Jupiter for at least 2 years, during which time it will pass by many of Jupiter's moons hundreds of times closer than the Voyager craft could in 1979.
For instance, there is a moon of Jupiter called Europa, which is ice-covered rock. It's the size of our own moon. It's the smoothest surface in the solar system. It's been suggested that we're looking at ice pack on a liquid water ocean. Galileo may reveal to us whether or not indeed that is ice pack on a liquid water ocean. If there is another ocean of liquid water still extant in the solar system, besides here on Earth, because of the importance of oceans in the origin and evolution of life here on Earth, I can't imagine we won't want to return to Europa, down to its surface, trying to somehow seismically examine the interior of Europa, and eventually, through that surface, down to the ocean, if it's there.
Yes, Jupiter is very interesting, and we would like to do that. So it's a competition between these priorities. We have to choose. We cannot do everything, perhaps, so that we have to choose. And there, probably the international sharing of the work would be quite important, effective.
Another probe in the Galileo type class is Cassini, which will go to Saturn early in the next century. This spacecraft will provide very detailed studies of this highly complex planetary system and stay in close orbit for several years. The Cassini spacecraft is a joint project with the European Space Agency. The goal of this mission will be to send the spacecraft into orbit around Saturn and then drop a probe into the atmosphere of Titan, Saturn's largest moon.
Titan is as large as the planet Mercury, And yet it's in orbit around another planet, so it's actually a moon, but it has a very substantial atmosphere, unlike Mercury itself. The atmosphere is 80% nitrogen, like here on Earth, 60% higher pressure than here on Earth, but unlike Earth, no oxygen, just methane, natural gas, which sunlight and other radiation is converting slowly but surely into very complex hydrocarbons and organic materials, which are raining down on the surface of Titan. And the probe will sample the organic chemistry that is occurring in Titan today, which may resemble in some important ways the organic chemistry that occurred early in the Earth's atmosphere before life evolved.
The second type of space probe is part of what's called the New Millennium Program, which is to develop the technology to build very small and inexpensive spacecraft. Some probes are ready to be launched, while others are still in the planning stages.
NASA is undertaking a revolution driven by the information age. It's allowing us to build our spacecraft much smaller, much lighter, and so much less expensive, and also to be much more productive. We think we're going to have a factor of 10 on weight, and cost, and on productivity. And this is going to allow us to do much more science.
Miniaturized probes would make new kinds of missions possible, ones which may have only one or two specific functions and which could travel to remote parts of the solar system and beyond. The Mars Pathfinder, first of these robotic missions to the Red Planet, will arrive and land on the Martian surface in July 1997.
It plunges directly into the atmosphere, going 17,000 miles an hour, slows down with a heat shield, parachute comes out, slows it down, some rockets fire to slow it down some more, and finally stop. And then Pathfinder opens up like a flower, and there's a rover sitting on one of the petals, a little rover this big, like the one that's behind me. It's a full-scale model. And so when it does that, it's going to explore a little area of the surface of Mars, maybe 100 meters around the lander.
In September 1997, the Mars Global Surveyor will arrive at Mars as well. It will fire its engines and begin circling Mars in a polar orbit that will allow us to study Mars from all angles.
You can't imagine understanding the Earth from having landed on the Earth in just one place. It's much too complex a planet. Mars is equally complex, and we need to find a way to systematically go back to Mars every opportunity there is with a series of small probes that can land on the surface, eventually drill down beneath the surface, looking for water, looking for any other evidence of the early era, left from the early era of Mars, when there was lots of water on its surface and where simple life forms could well have evolved.
In 2001, our lander is going to be landing in the ancient terrain of Mars, hopefully near an ancient lake bed. So we'll be able to see if there was ever, maybe, be able to see if there was ever life on Mars. In 2003, we hope to go with the Europeans on a project called InterMarsNet, where we'll be landing maybe 3 or 4 landers, and the Europeans will be providing an orbiter for a communication relay. And then in 2005, we're going to try to do a sample return, bring a piece of Mars back to the Earth.
Certainly one of the main themes has to be looking for clues as to the origin and evolution of life in the solar system. That is, looking for fossil evidence on Mars, or bringing pieces of Mars back so we can examine them here on Earth, to look for fossil evidence of life that might have evolved on Mars. Looking up near the polar regions where there still is frozen water ice, which may mean that there's a possibility there might be some residue, a life residue from that earlier era.
I think if life was there, it might be not too difficult to find evidence for it. It's much more difficult, in fact, to prove that there was never life on Mars. Because we can almost say, okay, we just didn't look at the right spots, we should have gone somewhat deeper, or we should have gone more towards the poles or more towards the equator. So to prove that there was really never life on Mars is much harder.
Now we have a planet that had an ocean which is gone, that must have had glaciers, enormous atmosphere, flowing water, and it's all now a gigantic desert. That's a sobering lesson of planetary evolution, but it's also far better than human imagination could ever have hoped for. And I've said it before, I don't know if there's any life in the solar system except possibly on Earth, but imagine that someone were to return with a robotic spacecraft a fossil acorn from Mars. And imagine what that would do to our imaginations and our children's imaginations.
If there is life on Mars, then there will be a simply fabulous expansion of the perspective of the biologist. Because all the organisms on the Earth, even though they seem to be different, are fundamentally the same. Their chemistry is all identical. And they're just wrapped in different kinds of wrappings. Us bacteria and us people and us plants, us protozoa, we're all the same on the inside. Now the question is, are Martian organisms the same on the inside as us? Is life everywhere, does it have to be the same as us? Or are we just one example of a vast array of possible kinds of biochemistries? Well, there's no way for us ever to answer that question, no way for us to determine the generality of life on Earth, except by looking for life elsewhere. And the nearest candidate planet is surely Mars.
Perhaps the boldest of all efforts is the plan to send 2 probes to the outermost reaches of the solar system.
We are also planning a new mission called Pluto Express to head on out to Pluto. Pluto is the only planet, the known planet in the solar system we have yet to visit, even once. So we are preparing plans for a mission that we hope we can launch early in the next century, which would rapidly move out to Pluto, which will be beyond the orbit of Neptune at that time. It will be a very fast flyby, very much like the flybys that Voyager had of Neptune's moon Triton back in 1989.
The age-old spirit of bold curiosity has now focused on joint international collaborative efforts to explore space together in many different exciting ventures.
Join us in a great dream, an American dream, a dream without end. First, for the coming decade, for the 1990s, space station freedom, our critical next step in all our space endeavors, and next, for the new century, back to the moon, back to the future, and this time, back to stay.
The International Space Station was conceived during the height of the Cold War. In 1984, we committed to building it with the Western Bloc, and we were going to beat the Eastern Bloc. With the Berlin Wall coming down, President Clinton asked NASA to see if we could bring the Russians into the International Space Station as a partner. And since 1993, the Russians have become a partner in the International Space Station, and they have brought with them an incredible knowledge in launch and human operations in space because they've been there for a decade with their Mir station.
The initial stages of this cooperative venture includes the exchange of astronauts and cosmonauts in joint efforts to learn more about extending the periods of time astronauts and cosmonauts can remain in space on board the Russian Mir space station.
The purpose of the Russian cooperative missions is to acquire a large body of scientific data aboard the Mir in long duration that we're currently not able to acquire, particularly in the medical area. You know, how does the long period of weightlessness affect the human physiology, and how does this data also pertain to diseases on the ground? The experiments involved looking at bone calcium and osteoporosis, changes in the immune system, changes in the blood system in general, looking at psychological aspects of long-duration spaceflight, a number of different areas.
This international cooperation has resulted in numerous short research periods on the Space Shuttle and Mir space station, during which time much valuable information has been gained. Now, the next step is the construction of a large, permanently orbiting international space station, which will be constructed and manned by crews of several different countries.
Space exploration is getting too expensive for any one country to do it on its own. And the International Space Station is a true cooperative effort. And I think that binding us together in space is going to also bind us together here on Earth. Looking at the Earth from space, it is truly a beautiful blue jewel of a planet in a black void. And there's no place else close by that we can move to. And I think that this joint cooperation in space is going to help us get along better on Earth, ensure that we have a safe environment and a safe planet to live on for many years to come.
The space station will be longer and wider than a football field, so just to give you an idea, it's going to be a really big piece of equipment, and it's all going to be assembled by astronauts and cosmonauts working together. The space station is an excellent example of international cooperation. We plan to build it starting in November of 1997, and we'll be building it through the year 2002.
It'll start out with a functional cargo block that'll be launched by the Russians, and then we'll carry up Node 1 via the space shuttle, which will add to the size to it and provide ports for docking other modules. And eventually we'll have a U.S. laboratory module, a habitability module. The European Space Agency is contributing a laboratory toward it. The Japanese Space Agency is contributing a laboratory for it. And it's going to be a phenomenal vehicle once it's totally assembled in space in a true international partnership.
We're complementary. The Japanese have tremendous knowledge in materials. The Germans have knowledge in optics. And we're all learning from each other, protecting our individual national needs for our economies, but in that remaining area, working together to better society.
And as we're building it, we'll have astronauts on board who will begin the scientific research. And the scientific research will continue while the station is being built, and then once the station is fully built, there will be 6 scientists and astronauts up there continuously working on these life sciences and these microgravity sciences, really trying to understand this unique environment up in space.
In respect to materials processing and other definite kinds of materials processing, such as protein crystal growth, such as large growth of crystals, some of which can be performed only on a place like the space station. I think we're going to learn a lot from better optics through containerless processing. And there are many other areas. Maybe we can use the space station to even manufacture crystals like gallium arsenide much more pure, so that we can develop the computers that we need today that are 100 times faster and 100 times smaller than the computers that we're now using.
So it's an orbiting laboratory. It's also a platform, and we can use that platform to study the Earth with certain instruments that complement those on other satellites. It's a platform that we can also complement other instruments in space for looking out away from the Earth. And it's, I think, an intellectual platform for the exploration that has driven this species since it first arrived, and that is the acquisition of knowledge and information and trying to determine where our boundaries are.
The benefits to humanity of having an international space station are countless. It would mean much enhanced and improved mapping of the Earth, weather forecasting, crop surveying, and detecting of new mineral deposits. These new developments are all vital to improve the efficiency with which we use the Earth's finite resources. In addition, to prepare for deep space travel, many more new studies could be made on the effects of weightlessness on the human body. Beyond that are the many as yet unknown benefits and advances in technology that constructing such a space station would result in. The possibilities are endless.
As a planetary explorer person, basically I think that we should use the space station to develop our ability to live and work in space. You need to learn how the machinery operates in zero gravity for long-duration space flights if we're ever going to explore the planets around the solar system, and we're going to do it sooner or later.
What we hope to do from there is to go on to exploration, and hopefully we can use the international cooperation model that we developed from space station as the foundation. And so as humans together we can go out and explore Mars, go back to the moon. There's a lot of exciting things that we can do together, pooling the resources, the strong points of all the different countries.
The bottom line is humans will always explore. And now we have set up an excellent infrastructure to continue to do that. We have set up a shuttle transportation system. We have been to the moon. We have started working with Russia on space stations. And of course the ultimate result of that is to use that as a platform for going on to explore other planets. And you can't just do it in one fell swoop. You can't just say, okay, here's a spacecraft, now go to Mars. We have to do these things in stages. And the space station is the next stage for humankind to learn how to go exploring beyond our own Earth.
Coming down at 2 feet, you got plenty of gas, dude. Hang in there. 30 seconds. 18 feet, coming down at 2. He's got it made. Come on in there. 24 feet. Contact light.
Roger, copy contact.
Pro.
When the astronauts of the Apollo missions first landed on the moon, they were like Columbus landing on the shores of the New World. Columbus promised wealth and knowledge beyond imagination to his sponsors, the King and Queen of Spain. Imagine what would have happened had no one followed Columbus to the New World. The same could be said for the question of whether or not humankind should return to the moon. We already know of the tremendous scientific and exploratory value the moon has to offer, but it would be no easy task. It would be yet another challenge to our abilities and talents as pioneers and explorers.
I thought when we left the moon that we'd have a base up there in a couple of years, but we didn't do it. I think it's time for us to look at going back to the moon now. There's a lot of things that we can learn about the planets that we don't know with human beings. Sure, we have a lot of problems here on Earth, and sure, they need to be solved, but they're not going to be solved by not expanding our knowledge, and that's what space exploration is all about. Expanding human knowledge is just fundamentally critical for people right now.
We'll go there to develop resources. We'll go there to emplace new scientific observatories of tremendous capability on the back of the moon, where radio waves from the Earth are not penetrating. We can put the giant radio telescopes, the Arecibo telescopes of the future will be in lunar craters on the far side of the moon. It will be a place where we go for many different research purposes.
I think colonization has to be based on economy, and if it's not based on economy, it won't happen, because any colonization based on a political imperative will have a short lifetime, depending on what the political winds that come and go. The only long-term imperatives for any sort of major activity are economic and religious that have caused long major movements to occur. And so we have to find some sort of economic reason to be in space, or else we will not be there for long-term tenable reasons. And people are looking for those.
Any long-term lunar colony would have to be completely self-sustaining and enclosed to protect its inhabitants from deadly ultraviolet rays from the sun. There are a variety of concepts currently proposed, but almost all of them would start out using materials sent from Earth. Then, using lunar soils and so forth to build perhaps circular dome devices, life support systems, and hydroponic greenhouses for growing food. New technologies would have to be developed to provide for a completely efficient biosphere.
Biosphere really means the kind of an atmosphere in which the air we breathe, the water, and all of our waste products are recycled and the same way they are on the surface of Earth, used again to support continuing human activities.
If you're going to live off the planet Earth permanently, you cannot always import your life materials from the Earth. You must learn to live off the land. Then the question is, what are the resources and how do you use them? And the moon is not a particularly good place for resources. It lacks a lot of the things that we take for granted for sustenance of life, such as the life-giving elements. They are there in great abundance, but in very dilute concentrations.
Perhaps the greatest challenge facing a lunar colony will be the development of all the technology necessary to create a constant source of food and sustenance for the inhabitants.
If we can indeed sustain these kinds of colonies in space, we're going to have all sorts of messages for how we can grow food on Earth in brand new ways in the future.
It forces us to work in a very disciplined and an extremely imaginative way under circumstances where absolutely impossibly difficult, and develops our intellectual, technical sinews so that we can do wonderful imaginative things. It is the desire to do difficult and innovative things that causes us as human beings to be creative and to be more responsive and to understand. The resources are the human beings, and the challenge is the chalice which drags us to exercise ourselves to superior levels of performance.
And the pioneering here is in the technology that brings the nutrients to the roots of these plants. This is different from the way we do it on Earth, but in the Moon or Mars, we need to have this closed ecology cycle. So all of the air that we breathe, the water cycle, the food cycle, is all moved in an engineering fashion to keep life going on very remote from the Earth's natural biosphere.
Exploration of the moon is still in its infancy, and there is little certainty as to the best use of its resources. No one today can even conceive what the benefits from such a lunar colony might be until the effort is made to establish one. One such potential source of exploitation has been the possibility of mining an isotope of the element helium from the moon's surface that has been accumulating there from the solar winds for billions of years.
Based on what we now know about the moon, there are some possibilities with the mining of helium-3 from the surface of the moon to bring back to Earth as an energy source. That scenario assumes that we will be basing our energy generation probably in the middle of the next century on nuclear fusion reactions which use helium-3 along with deuterium in reactors which are radiation-free and don't have the radioactive waste that we are now concerned about with nuclear fission reactors. If that's true, then the Earth is not a rich source of this rare isotope of helium. It does, however, exist in the soil on the lunar surface.
The shipping costs are rather large, and to ship the rocks back here to process it would be enormously expensive, and to process it on the moon would mean establishing enormous factories.
People have done fairly simple calculations that show if you were generating all the nation's electrical power by this method, what the price of this fuel would be, what it would be worth. And you can find that you can go and set up a colony on the moon and mine the helium-3 and bring it back to Earth and make a nice profit under those assumptions. But the assumptions are very important to understand, so it's a possibility.
By the early 1970s, the American space program had researched and developed plans to send manned missions to Mars. 2 unmanned Viking probes were sent to the Martian surface to take photos and to test and analyze the Martian soil for the presence of water and possible life forms.
We see now an extraordinary increase of the performances of the computers. And a lot of us believe that in 2020, 2030, we'll have computers which will have a computing power not far from the computing power of the brain, of the human brain. And so all the actions which could be made by man when they would be on Mars may possibly be done at that time by computers.
I would not say there will never be a man on Mars, because so far I think man and woman of course, have always done what in principle is possible. The Earth was explored up to high geographic latitudes, and the oceans were explored as far as down to the absolute maximum depths. So I'm actually more or less sure that also man will once start to go to Mars.
A common question in the space program is always the tension between, do you need people or should you just use robots? People are adaptive. When something happens, they're able to react like robots can't. They have versatility and flexibility and manual dexterity. So there are things that people could do that robots can't. But we will not send people until it's economical and the potential for scientific or economic benefit is high enough. And that's the approach we're using. Yes, we need people. Yes, we need robots.
The robotic program and the human exploration program really work together in the sense that when you send a human being to, say, Mars, which I think will happen, certainly, hopefully not too far into the next century, we would like those human beings to do the most important things they can do during their stay on Mars. That we will know because the robots will have explored Mars well enough that we know what the most important questions are that the astronauts can help us answer, and we will know where the most important places are for those astronauts to visit. So the robotic program will lay the groundwork in terms of understanding the Mars so that we can be most effective in our initial brief human explorations of that nearby planet.
Sending astronauts to Mars has become the new focused goal and dream of the American space program. As President George Bush announced in 1989, humanity had entered a new age of exploration and should make every effort to send manned missions to Mars. As we have seen from the space effort made over 3 decades ago, this space effort will power another revolution in science and technology, boost the economy with spin-off developments, reanimate the educational system with all the new information and excitement about future discovery, and so in turn raise national morale and spirit.
When are we going to go to Mars? The Commission is not recommending an Apollo type of manned piloted expedition to Mars. What we see rather is a steady buildup of activities that will naturally lead to the establishment of outposts and bases and people on Mars.
When we get to human missions, it's almost certain we're going to have an international endeavor, just like International Space Station Alpha. I mean, that's got Europeans, it's got Japanese, it's got Russians, it's got US, and I think that's the way we'll be going to Mars with people.
Any serious effort to get a manned mission to Mars would no doubt cost several $billion, and serious questions would obviously arise whether the benefit of such a mission would be worth the cost. Perhaps the most compelling reason to go to Mars is the distinct possibility that life may have existed or still may exist there.
A lot of people talk about going to Mars and living there because there's this association that maybe there was once life on Mars. The difficulty with that scenario is that currently it is much more difficult to get to Mars than it is to get to the moon. You have to travel for a much longer time. When you're there, you are basically isolated from everybody else for a period of 2 or 3 years. It's like the circumglobal voyages of Magellan. You don't see home for a long time, and nobody can help you.
By about 2018, we hope to be able to field a human mission to Mars. We haven't actually worked out the details, but 2018 is a nice time frame because you've got the space station that's going to be operational in a few years. people need to live and work on the space station for a while to see how much zero gravity they can stand, and they need to be able to understand something about partial gravity.
There's several areas in which I think we need to look at closer before we talk about making a long trip to Mars, or before we talk about living for several years out in space as we make this trip. And that's, we need to look at radiation effects, will be a big thing. We also need to look at the calcium loss in the bones, and we need to look at the cardiovascular system to make sure that after an extended period in weightlessness, the cardiovascular system will rebound and your heart will function properly when you get into a gravity situation.
We need better rockets to get us to the space station economically, and those same rockets can be used to take us to Mars. So by 2018, we ought to have the technical infrastructure in place and a sufficient understanding of Mars so that we know how to send people there.
I can't think of anything worse than making a great trip out to Mars, and you spend a year or whatever getting there, and then you land and you say, great, here we are, we've got human beings on Mars, and then they can't get up and walk around and explore, So that's where I think a lot of the life science research is directed, is to make sure that when we do land on Mars, that we'll be able to live and function there.
Within 20 years or so, if Mars turns out to have resources that we can use, we ought to be able to start building up settlements and actually starting to settle the planet and learning to live there. So I think in 50 years, if we find out the technology base and we do everything carefully, we ought to be able to get there.
So you have to have a highly reliable technology that's failure-free or repairable, that you have searched every contingency so that you don't die while you're there. And then under those circumstances, you can live on Mars, and there's some advantages because there's an atmosphere that has a lot of carbon dioxide and little of anything else, but you can do things with it.
Now on Mars, we know there's water because we can see the polar caps. And the water, in fact, when Viking did an analysis, they found that the dirt was full of water. In fact, it was so full of water it saturated their instruments, so we don't know how much water there is. But water has been somehow absorbed into the soil. And so there's water, there's oxygen can be made out of the carbon dioxide in the atmosphere. Oxygen can be gotten out of the rocks because we know they're iron oxide. And so you got water and oxygen, and you can put out solar arrays because it's reasonably close to the sun, so you can use solar arrays feasibly. And so you've got power and oxygen and water and dirt. What else do you need? Now, you don't have that anywhere else in the solar system except on Mars.
If we could find ways of living off the land on Mars, if we could find resources there to make value-added materials and resources to live, economic resources to bring back to Earth, we could then perhaps think about 50 years from now, transitioning into sustained human presence.
It always happens in the history of science that as your perspective broadens, you learn more about what you left at home as well as what you went out to seek. And so it may be that in the long term, the greatest boon to science and to mankind from the exploration of Mars will come in terrestrial biology. It's just a speculation on my part, but I think there's a good chance that that will be the case.
When I talk to kids at schools, they often ask me if I've ever been to Mars. And of course, they don't realize that the shuttle doesn't travel to Mars. But I love turning to them and saying, I'm probably too old to go to Mars. However, someone in this room is young enough and may possibly have the opportunity to go to Mars. I won't go, but you will. And then to see the looks on their faces when I tell them that, and making them aware of the opportunity they have ahead of them, really gets me excited and gets them excited. And that's a goal I would like to instill in people that are younger than me at this time.
Throughout history, humankind has had to make the choice whether to stay someplace where everything is safe and predictable, or to move on and explore new frontiers. Time and again, people have made the choice to seek new challenges and to explore new frontiers. Humanity may continue to make war, to fight, to bicker, and to struggle, but will never be able to resist the challenges that space exploration has to offer.
I've always felt that we're in a war, the whole human race is, and whether we know it or not, and I always call it we have a war on poverty, a war on crime, a war on drugs, but the war that we really must solve if we're going to be successful in the next century is a war that nobody knows we're in, and that's a war on ignorance. If we solve that war, we can whip all the other things in the process. That's what space exploration is all about, expanding our knowledge of what's going on around us. And boy, it's in its infancy, and I think it's important to do it now because I don't know how much time we've got, the human race does. We need to get smarter, and we need to learn better how to control our destinies, and I think space exploration is a key to that.
There are very strong philosophical reasons for moving to space, to learning how to use resources off the Earth and prepare ourselves for extraplanetary living. But you have to face up to the practical problems of garnering the resources, which are immense, in order to do this exploration. And you also have to have organizations and institutions that are responsible enough to use those resources wisely so that the public trusts them in their use of their expenditure of large sums.
There's a question I get asked many times. Why should the general public be interested in NASA exploring Mars, other bodies in our solar system? It's not NASA's program. The program belongs to the American people. NASA is about the future. NASA is about understanding our universe and solar system to better understand our own planet. We have to look out into the future for the next generations. And NASA is one of the few things our society does that reaches out 10, 20, 30, 50 years.
It has been said that knowledge is power, and with the knowledge we stand to gain about the secrets of the universe, we, as a people, will have the power to shape our destiny, a destiny that may find the whole of humanity as settlers of the space frontier.